All right, this is the second part of molecular geometry. We're really going to be going through 11.9 and 11.10, and it will finish us up, but I don't know if I'll be able to do this all in one video, so there may be two parts to this. When we're talking about molecular geometry, we're talking about the actual physical shape of the molecule. We mentioned that in the last video. And there is a really important table in your book. It is on page 360, and I have kind of recopied it up here. It gives us the 5 possible geometries when we have an atom that has an octet. Just so you know, there are some atoms that don't have an octet. In fact, your book will mention them. The element beryllium only ends up with 4 valence electrons to be stable, and boron needs 6. And so those sometimes will get spoken of, but don't worry about those. We're going to deal primarily with this up here, with a full octet. The only other exception would be hydrogen, which always has 2, but we're always talking about the central atom. And it turns out that there are 5 cases. Now, if we were in school, I would actually talk to you about a 6th, but because I'm going to try and stick very close to the book talks about 5 cases. And the 5 cases are on your table. This is page 361. So right here, case 1, 2, 3, 4, and 5. And what they do is they break these down into how many pairs of electrons have to be arranged around the central atom. Now, remember that when we talk about pairs of electrons, I call those electron regions, but what they are is the bonds plus the lone pairs. The bonds could be a single, double, or triple bond. So, for instance, carbon dioxide, which we mentioned before, would fit in here. There are 2 bonds and no lone pairs, carbon dioxide. If I had NH3, that would be N, and I probably should do this. This would be our Lewis structure, which is still important. And as a result, you would have N, H, H, and H, and you would have a lone pair of electrons. I would do that as an unshared pair, and this would actually be down here. It would be 4. So this next column tells me how many pairs of electrons. You notice there's only 3 possibilities. We could have 2, 3, or 4. Now, the next one counts the number of actual bonds. So let me actually do this. We've got this. We have this one. Let's have as well, say, sulfur trioxide. And let me do in here carbon tetrahydride and water. And I've done the Lewis structures here real quick. This one has 2 electron regions. This one has 1, 2, 3, 4 electron regions. This one has 1, 2, 3 electron regions. This one has 1, 2, 3, 4 electron regions. This one has 1, 2, 3, 4 electron regions. So if I was doing my second column, this one would have 2. This would have 4, this would have 3, this would have 4, and this would have 4. The next one talks about the number of bonds. And the number of bonds are exactly that. A bond actually holds 2 atoms together, if you remember. So this one would have 2 pairs, but it would have 2 bonds. So regions or pairs, bonds. This one has 3 bonds. 1, 2, 3, this one has 3 bonds, this has 4, and this one has 2. And that should help to explain this over here. And now we have the name of it. They call this the electron arrangement. I call it the basic geometry, but we'll use their words, electron arrangement. Anything which has two pairs of electrons is going to be linear. Anything that has three pairs of electrons is trigonal planar. If you remember, that would be this. This is linear, like that. Trigonal planar, we come in and we have this shape. And tetrahedral, a little trickier, but we end up with something like this, where all of the bonds are at 109.5 degrees. And that would be anything that's here, tetrahedral. So we have linear, trigonal, planar, tetrahedral. If there are four bonds, I should note that it's this column right here that is giving me this column here. Notice, 4 bonds, we call that a tetrahedral basic geometry. 3 bonds is trigonal planar, 2 bonds is linear. They call this a ball and stick model, but it's actually just the way that we look at this. If we were looking at the way these are arranged, and by the way, my line here and the line in your book could be a double, single, or triple bond. We're not distinguishing at this point. A has 2, because there are 2 pairs, 3 because there's 3 pairs, 4 because there are 4 pairs, 4 because there's 4 and 4 here. So this column, I should do it this way, this column gives me this and this. And now the bond angles we talked about before. Bond angle is the distance between the bonds. It's not the distance between it and the molecule. It's from this bond to this bond, 180 degrees. If we have 2 of these, they will be at 180 degrees. The 3 of them will be at 120 degrees, like that. 120, 120, 120. And then the 4 will always be arranged, as we've already mentioned, with 109.5 degrees as our tetrahedral geometry. This next column, the molecular structure, comes from a combination of these 2 columns. Produce this. A molecule that has 2 pairs is always going to be linear. 3 pairs is always going to be trigonal planar. But 4 pairs, it'll depend on how many bonds. If it's 4 and 4, it's tetrahedral. But let's say that we don't have, we have NH3 here. This one now has 4 pairs, or 4 electron regions. Whoops, sorry about that. 4 electron regions. But this doesn't have an atom on it, and so our geometry looks like this. I'm going to pull this down so you can see it just a little bit better. Okay, I don't know if you can see it or not, but this is not a flat molecule. In fact, this is a tetrahedral as well. Forget about this stick on top, although it still is there. Sorry about that, I keep dropping things. But this one has a top here and then 3 points. And basically it is also a pyramid. But I can't call it tetrahedral because it actually is a different shape in a sense than having this one up here. And it turns out, I've marked it, these bonds actually get pushed a little closer together. This is a more intense electron region, 107 degrees, but your book says 109.5, so we'll use 109.5. This is called trigonal pyramidal. Now, trigonal pyramidal is an interesting word. Trigonal means a triangle. Pyramidal means it's a pyramid made out of triangles. And if you look at it, there's a base, which is a triangle, and each one of the sides. Turn it this way so we can see it. Each one of the sides is a triangle. But that's exactly what a tetrahedral is. So this is a fancy way of saying this is a another molecule that has almost the same shape as this one. And then finally, we have what is called the linear molecule. A linear molecule, not a linear, a bent, excuse me, not linear, bent or V-shaped. If I take a water molecule only has it has 4 regions, but it only has 2 bonds on it. And the molecule ends up looking something like this. We call this a bent molecule. Your book also calls it V-shaped. V-shaped certainly makes sense. Bent, I don't know where that comes from, although it does look like somebody took a linear molecule and bent it. This molecule actually has a bond angle of 104.5. Again, your book's going to say 109.5, but it's actually 104.5. And it has a flat, it's a planar, but it is definitely a bent molecule. The Lewis structure for this you'll always have A with 2 B's. Usually these will be double bonds. Excuse me, I'm kind of off the screen there. I'll do it this way. These is 3 bonds, and one of these could be a double. 4 bonds, 3 bonds and a pair, 2 bonds and 2 pairs. And then the example that I've used here are the ones that are over here. For this one, carbon monoxide or carbon dioxide, ammonia, I actually did this one. This is the sulfur trioxide. This one is here, and this one is like this. Now, one other thing I should mention, there are other types of molecules out there. One of the most common ones that will cause trouble for students, and it shouldn't, would be, say, something like oxygen, because it's not going to fit this pattern. First of all, you don't have a central atom. This is called a diatomic or 2-atom molecule. Anytime you have a diatomic molecule, and by the way, it would look like this. If I ask, what's the geometry of this? It is linear. You say, well, how do you know it's linear? Well, it's real easy. I have an oxygen and another oxygen, and they are stuck together. Do you remember geometry? How many points does it make to make a line? What does it take to make a line? 2 points. This is 2 points. Any diatomic molecule will always be linear. Doesn't have to be what we would call diatomic, the same atom twice. If I had a CN with a -1, that's a cyanide molecule, that'll be this. And we would call that a linear molecule. Now, the assignment on this is actually fairly lengthy because this is where we need to spend some time. And so what I'm going to do is go through some of the problems. If this cuts off, I will post problems, but let me just take you through some of them. You're going to do these problems for me. 73, 74, 76, 77, and then 78 through 88 even. So really it's 74 through 88 even, and I also added 73 and 77. Let me just do some example ones that are like it. The odd problems right in front of them are the same type of problems. So on 79 it says, for the indicated atom in each of the following molecules, give the number and the arrangement of the electron pairs. So 79A, let's do 79B. It says NCl3. What you're going to need to do is the Lewis structure here. And then these will be all the way around. We are only interested in the central atom. So if I take and draw this out, it's going to be N, Cl, 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 and I would do like that. And so we would say that the the number and the arrangement of the electron pairs. There are 1, 2, 3, 4, and it would be tetrahedral. That's what they're after. So it's this column, how many pairs, what's the name of it. On problem 81, it talks about the VSEPR theory. And I just realized I forgot the VSEPR theory. So I'm glad we did that. So let me quickly